evening, everyone, and thanks a lot for coming. Before starting, I want to thank the organizers for inviting me to give this talk. And I'm going to talk to you about the brightest objects in the universe, which is my personal research topic, which we can call quasars. So quasars is actually a general term that we can use to encapsulate a lot of different astronomical objects. But this word will suffice for this talk. So a little bit of history. The word quasars comes from quasi-stellar, so very close to a star. As an example, we have here an image that was taken with the Hubble Space Telescope in 1996, where we can see two things that look very much alike. One of them is a star, and the other is a quasar. So you can see how these two can be confused. And this is from the Hubble Space Telescope. Imagine with a telescope that is on the ground, it's even worse. So the main difference here is that the star is relatively close to us in our own galaxy, while the quasar can be thousands or even millions of times farther away in the center of another galaxy. So tonight, I'm going to speak a little bit about the science of this thing, but mostly I want to let you know why I think that quasars are so awesome. For example, I know that many astronomers, astrophysicists were amateur astronomers when they were younger. Well, I was never one. I used my first telescope when I was already in the Masters. I decided that I want to become an astronomer on the 6th semester of college, out of 8. So, and it was reading about these astronomical objects that gave me the passion to say, this is what I want to do the rest of my life. So, just to, as I said a moment ago, the quasars are really, really far away in comparison to the stars. But even then, as we saw in that image, are similarly bright, which means that these things should produce enormous amounts of energy. So to try and give you a little idea of how much energy, I'm going to start with, this is not our galaxy, but it's very similar to our own galaxy, the Milky Way. Our own galaxy has around 10 billion suns. Produces the energy equivalent to 10 billion suns. Now, one quasar produces the equivalent of hundreds or even thousands of galaxies like ours. So that in itself is, I think, is remarkable. But not only that, the engine, so to speak, that produces all this energy is encapsulated in something the size of our own solar system. Now, probably some of you don't have the scale of what a galaxy to our solar system is. So to give you a quick example, I'm going to scale things. Let's imagine that our solar system with all the planets is the size of a compact disc. We all know a compact disc. So our galaxy, in comparison, will be approximately the size of the whole planet Earth. So we effectively have something the size of a compact disc that is producing as much energy as 100 or thousands of times of something that is the size of the entire planet Earth. I don't know if you can imagine the scale. So that is one of the first things that that called my attention when I started reading about these kind of objects when I was in college. So now, obviously, once I was hooked on, okay, why are these things so bright? Then the next thing I wanted to know is how does a quasar produces such amounts of energy? What kind of process what is happening there? Well, the answer is thanks to a black hole. But not just any black hole, a supermassive black hole, which means a black hole that has millions or even billions of times the mass of our own sun. So I was like, okay, so we have black holes, we have these supermassive black holes. As of right now, it's mostly accepted that most, if not all galaxies, have one of these supermassive black holes in the center. So what is the difference between a normal galaxy and a quasar if all of them have these black holes? Well, the only difference is that in quasars, these black holes are eating. They are eating material. They have material that is falling onto them. And well, I wanted to put a video here, but for some reason it didn't work. I guess because my computer is way too old and the new ones cannot convert the format. So I just have like the image at the end of the video. Let's imagine that, okay, let's see if I can make this thing work. No. This? Oh, forget it. Let's imagine let's imagine that all of this, it's in the same plane. Like the video was just showing how everything was in a single disk. It was just moving. So I'm not going to explain all of it. I just want to let you know that here is the black hole. And around it, all of these things is material that is orbiting or moving around the black hole at incredible velocities. I'm talking thousands of kilometers per second. And this material is heated to millions of degrees. And if any of you has seen either live or on the internet, a cherry red piece of metal, you know that when something is very hot, it emits a lot of light. Well, it's the same with this. This process is called accretion. And I was fascinated by it because it can produce incredible amount of energy. And just to give you an idea, I'm gonna compare this process to something that we're more familiar here on planet Earth, which are chemical reactions, specifically fusion. So, for example, a hydrogen bomb, fusion, nuclear fusion, works by combining 4 hydrogen atoms in 1 helium atom. And then it releases energy. Now, the reason why this releases energy is because this helium atom that we produce actually weighs less than the sum of the 4 hydrogen atoms. So the rest of the mass is directly converted to energy. And probably some of you have heard about this guy, very smart, Albert Einstein, that had this equation, E equals mc squared, that basically tells you that mass or matter can be converted directly into energy. So this process, which is one of the most efficient that we have on Earth, converts only 0.7% of the material involved into energy, 0.7%. While the accretion process that I was talking about converts around 10%. So it's over 10 times more efficient. And that is the main reason why it can produce such amounts of energy in so little space. So that's the second thing that caught my attention when I was first reading about these things. First, okay, they are very bright, impossibly bright, the brightest objects in the universe. Second, the processes that get you this much energy. At the time I was even thinking, maybe we can do something like that to produce energy here, I don't know. I was just thinking things. So these two things then led me to the rest. What kind of energy it is producing? It's producing light, but it is producing all kinds of light, what we call the electromagnetic spectrum. Maybe some of you know, maybe some don't, that radio waves, microwaves, ultraviolet, X-rays, gamma rays, all of these are light, just as the one that we used to see. The only difference is that these kinds of light have a different energy. And that's actually the reason why ultraviolet light and X-rays hurt humans, because they are a higher energy than what we're used to. So, and quasars produce all of it, absolutely all of it. And just to give you an idea on how hard that is, let's say that we put all these types of light in a movie film. The movie film will be, let's say, a length of 4,200 kilometers. And the visible light, the one that we can see with our own eyes, will be only 3 centimeters of the entire length of this film. So by trying to see things with only our eyes, we will be missing a lot of what it's out there in the space. That's why we build different telescopes. That's why antennas can be used as telescopes, even though they receive radio waves. That's why also we need space telescopes, because there are some of these kinds of light that the atmosphere prevent to reach Earth, and things like that. So this was the third thing. These 3 facts were the ones that, after learning about them in college, I decided this is what I want to do with my life. I want to be an astronomer. I'm fascinated by this. I want to know all the physics, all the intricacies of this type of objects, of these processes. It's never ending. It's just amazing. And actually, most of my colleagues in the BLBI group at the Max Planck Institute for Radioastronomy study these kind of objects. So now that I told you why I became an astronomer and the things that interest me, as I said, these things are bright. Processes very complicated, and they produce all kinds of energy. Now, I want to talk to you about something that most of you may want to know, about the thing that is the engine of these things, which is the black hole. So, a black hole, the textbook definition, is a region of space where light cannot escape. But what does this mean? In order to explain it to you, I need to explain the concept of escape velocity. So, escape velocity is the speed that an object has to reach in order to escape the gravitational pull of an astronomical object. For example, a rocket, in order to escape the Earth's gravity, needs to travel at around 11.2 kilometers per second, which is a lot per second. So, in comparison, a black hole, by definition, should have an escape velocity of equal to the speed of light. So that's a big jump. So how can we imagine a black hole in terms that we can, let's say, understand? I mean, even astronomers don't exactly know all that is inside a black hole, or most of it we don't know. So I'm gonna give an example. Let's say that we take our Earth with escape velocity at surface. Let's remember from middle school that gravity acts depending on how far you are from the thing that is exerting gravity. So this 11.2 kilometers per second is the escape velocity at the surface of the Earth, which is over 6,000 kilometers from the center. So if we wanted to have the Earth and we shrink it so that at the surface we have escape velocity equal to the speed of light, this will be the Earth, something that in diameter has 9 millimeters. If we wanted to construct a black hole with the mass of the Earth, it will be something this size. So, and also you can imagine how dense this thing is. And I think these are fascinating objects. We have held at the Max Planck Institute a couple of conferences exclusively on black holes over the last few months. I've been fascinated by what people that do equations, theoreticians, etc., have come to say to us. All the different theories of what black holes are. Like, yes, we have the textbook definition, but what is inside? We don't know. That's the answer, sadly. We still don't know. We have theories, but we cannot know for sure what is inside. But I think that not knowing and the fact that we can still keep studying these objects, the fact that there's still things that we don't know, well, for starters, it gives me a purpose because I want to learn. And second, we have a job because of that. At least the astronomers do. So, thank you. Well, this was all, most of what I want to tell you. How these objects, why these objects fascinate me so much, why I made them the topic of my research, and why I think it's something that if any of you ever want to learn some more about extreme physics, let's say, or astrophysics, it can be something that you can start with. It's just to read it. I think they are fascinating.